Good evening. Let's try again. Good evening. I want to make sure that Mr. Corbin knows that there are some very excited young scientists here. So let's make sure that our energy level is high here. Well, good evening and welcome to the Young Scientist Roundtable. Let me ask you quickly a question. How many of you attended the last Young Scientist Roundtable that was held in Wayzata High School? Okay. Anybody of you, any of those who attended the program thought that it was less than excellent presentation? Just a question. You can raise your hands. Okay. But yes, those who attended were very fortunate in my judgment. It really was one of the most outstanding events that we have held in last 26 years. So this evening we have got a speaker who has come here, driven here from Iowa. Mr. Jared Corbin is R&D manager at Sethness Products Company in Clinton, Iowa. He received BS in chemistry from St. Ambrose University in Davenport, Iowa. He then completed MS in chemistry with an emphasis in analytical and physical chemistries from Kent State University in Kent, Ohio. He did additional graduate work at South Illinois University in Carbondale, Illinois, in material chemistry prior to joining Sethness in 1998. Sethness is a Chicago-based company. It has been a world leader in caramel color for over 137 years. It offers liquid and powder caramel colors for a wide range of food and beverage applications. As R&D chief, Mr. Corbin manages all aspects of innovations, product development, process development, and technology transfer to Sethness global locations in France, China, and India. Just about 2 years ago, I was at an event in Dallas where I met the sales executive from Sethness Products Company. Over the dinner, we were talking about it, and I told him about Young Scientist Roundtable, and he told me that if this is simply a phenomenal concept that you are running there, as a leader in our own technology, I think we're obligated to help you. We will arrange a speaker for you. So 2 years later, the net result is we have Jared Corbin. Mr. Corbin will share his expertise in a talk with the title, The Art and Technology of Caramel Color. Mr. Corbin.
Thank you, Pino, for an excellent introduction. Thank you all for attending this evening. While I'm not going to be talking about rockets and faraway places, we're going to talk about food. So I hope everyone's had, a good meal tonight. Sure. I'm sorry about that. Is that better? Yes. Is this better? All right. So the art and technology of caramel color is quite a simple topic, but there's a lot of complexity involved with it. Let's see here. So just to kind of give you a brief overview of what we're going to talk about tonight, we're going to talk a little bit about the history of caramel, how did it come about. We're going to talk a little bit about the chemistry, but on very simplistic terms. The different applications, Vinod had mentioned that, it's used in a variety of different applications, but we're going to get, which one specifically. And these are food, and drink and beverages. So then lastly, we're going to talk about a little bit about how does one go about developing a new product? And then some of the current challenges that we're facing with our business. So, caramel history, what is a caramel color? Is it, maybe The issue that we have with caramel color is that some people think is very complex because there's chemistry involved. Actually, it isn't. It's very simple. It's very basic. We're going to try to not necessarily dumb it down, but put it on a very easy way of describing the process. So caramel color, what is it? Is it just color? That maybe someone sees in their hair? Is it a candy? That some people may, find, in their candy box. Or is it burnt sugar? It's just burnt sugar, but it's been used in both these kinds of applications. So, caramel color, was it used in? Most commonly, everyone sees pop, Coke, the Pepsi, the Dr. Pepper, the root beer. But it's a lot more than just that. It's in sauces, it's in gravy mixes, it's in cakes, it's in breads. I've also seen it in very strange things. No. The positioning of all the equipment, so my apologies on that. So, everyday reactions, what's a really good example of caramelization? Caramelization, or developing a caramel color, is basically what we call browning reactions. So browning reactions are anything that will obviously start turning brown. The easiest example, cut open a piece of fruit. Let it sit there. Expose it to the air, and it's going to start to oxidize and turn colors. That's the basic premise of what caramel color really is. It's about heat and time to generate color. Now, this is a very long process, right? Depending upon the humidity and the temperature in the room, it may take some time for it to start to turn color. So let's speed it up a little bit. This case, now we've got a pile of sugar and we got some acid. For some of those who are at the high school level and have already had maybe their first chemistry, my chemistry teacher back in high school actually did this demonstration. He put it in a beaker with the acid and it started smoking and started generating a lot of black color really quick. And it really grows really crazy. So these are two examples of caramelization, very minimal and very aggressive. And what we want to do as an industry is try to control it so that it doesn't smell burnt and it's actually a little appetizing instead of looking like rotten fruit. So other types of browning reactions that you may be used to. Well, brewing. If you had a cup of coffee this morning, maybe some tea, or watching a football game, maybe some grilling of some steaks, hamburgers. Anyone want some French fries? These are all different types of everyday kind of caramelization reactions going on. Things that are turning brown that you want to get to a certain kind of look or texture, right? Because you want it to look appeasing. That's the role of what caramel color is all about. So the timeline. So if it's all about cooking, caramelization's been around since the dawn of time. Ever since someone threw something on an open spit with some fire. That's how it goes. It wasn't until the 18th century, the late 19th century, early 20th century that caramel color started becoming commercialized, where using the color for a specific purpose. In this case, it was spirits and wines. And then it was then later expanded in the 20th century with the colas. All right. So with all this commercialization, we want to make sure everything's safe, that we're not doing things strange and different. So everything became more codified and regulated, so make sure that caramel color is always considered safe. This is kind of maybe how caramels were made back in the day. Guys standing over an open wok with a little bit of fire, cooking things along. All right, this is actually still used today, not in this form, but in this form. This is one of our, what we call our open atmospheric or open kettles. It's got a very large industrial mixer on it. It's got big open vents and everything. So this is not pressurized. We use heat. In this case, we use steam heat, but you can also use oil, gas fire, any kinds of things. The problems with this process is that it's an evaporation process besides color generation, and because of that, as you approach the end of the reaction, it becomes very thick and viscous, so that's why you need the very strong mixer, and you can only produce so much. So in this case, only about 200 to 400 gallons. You think that may be a lot. Let's apply pressure to it, where we're not evaporating now water off, and now we can jump it to 2,000 to 4,000 gallons, for doing a batch of caramel color. Well, who needs that much caramel color? All the pop companies. They go through quite a bit of caramel color. We're sending what we call tankers. So the railroad tankers that you'll see on the railroads, we fill those things up, and we're sending them off to Coke, Pepsi, and everybody else. So we also do spray drying. So we take the liquid caramel, we apply different patterns of heated air through it to evaporate it off. The use of the liquid over the powder is obviously liquid application, but the powders are very good for different baking applications or dry mixes. So, chemistry of caramels. Chemistry all starts off with something very simple. Chemicals, right? My job as a chemist, we're always trying to make something and turn it into something else, right? Isn't it what we're trying to do? We're trying to make gold. Well, my job is to make black gold. So you apply a little bit of energy to make a new molecule, right? To then have some kind of outcome. The problem with chemistry is the outcomes can be quite varied. Again, think back to the apple or to the pile of carbon coming out of the beaker. Those are pretty extremes. How do you control a little bit better? That's what we're going to kind of talk about. So a lot of poorly defined, multiple steps, a very huge amount of variety of outcomes. Now, but to make it simple, it's just sugar, right? And then we're applying a little bit of heat, maybe some chemical, to produce color. Now, again, this is very simplistic, but there was a guy who spent a lot of time on this. He was a French physician. His name was Louis Maelard. In the early 1900s, he figured out how all the special steps in caramelization was going on. In this case, he was dealing with what we call amino acids and sugar. Now, amino acids is basically kind of like a protein, but it's got readily available nitrogen. Nitrogen is very important for caramelization, for color generation. So my apologies that this looks very complex. You can hardly read anything, but this is trying to show, the extent to which caramelization really kind of goes through, and the understanding that Maelard, put forth into his thoughts. But just to highlight certain things that are kind of important. That I just circled there is the sugar source. The amine, which is the nitrogen, if you can kind of see the nitrogen there, that's the chemical that he's adding. To finally at the bottom, polymerization. It's basically as he broke down all the sugar and broke it all apart and rearranged things, now all the pieces are coming back together to form color. So again, the 3 steps: break down and transform all the carbohydrates, have everything come back together just to form color. Now, the Maelard reaction or caramelization is actually not the same. The Maelard reaction specifically uses amino acids. Caramelization doesn't. There's 2 different types of caramelization that uses nitrogen, and in this case we use ammonia. So the process still starts the same. So this is representing class reason 4 process, but the pH will swing. As you go to as the pH goes up, you're going to form certain other molecules, and as the pH goes down and go acidic, you're going to form other kind of molecules. All right. So again, there's the sugar. There's our nitrogen source. This is what we call class 3 process. On the other side, to be acidic, we have some SO2, also known as sulfite. It actually has an acidic side to it, paired with the ammonia to form the color, and this is what we call a class 4 process. Now, that's one difference between caramelization and the Maelard reaction. There's another difference where there is no nitrogen. In this case, this is going to be an acidic process. Again, we're starting off with the sugar. We can still use sulfite to form the color, to form a class 2 caramel, or we're not going to use sulfite whatsoever, still form color, and that's what we call class 1. Now, class 1s can also go, alkaline. So it has a different kind of reaction pathway. So again, we're going to start off with the sugar. We're going to form color, and that's still a class 1. But it still breaks down to the same simple process. Sugar, heat, maybe some chemical to form the color. So we've talked about that there's 4 classes of caramel color. They all use food-grade carbohydrates. And the carbohydrates I'm talking about are the simple sugars. One of them you're familiar with, table sugar. But that sugar breaks down to 2 other sugars, dextrose and fructose. And we're also allowed to use maltose and a variety of other things like molasses and some other carbohydrate sources to generate color while still applying heat. So the class 1s can be with or without any kind of chemical and just heat, or we'll use an acid or a base. The class 2s will be everything the class 1s do, but also with the sulfite. The class 3s will use everything the class 1 does, but then starts using the ammonia. And then the class 4s will be with the sulfite and the ammonia and everything of the class 1s. So it just higher and higher level of complexity, but it's necessary to generate more and more color and to get different kinds of functionalities for the caramel colors. So we talked about modernization. So in the 1980s, they finally decided to come up and identify the 4 classes. Prior to the 1980s, they actually had like 8 or 9 different classes, depending upon what area of the world you were in. And they were arguing back and forth, and so they finally decided on 4. Then later they came up with safety regulations and ways to manufacture it. And because of all that, the FDA, our federal government, gave caramel color the status called GRAS. GRAS means that it's safe. So generally recognized as safe, can be used in any kind of food products without any issue. That's the whole point. So the regulations. I'm not going to go into detail, just who governs us. The first one is the Code of Federal Regulations, the CFR. That gives us and tells us what we can make caramel color out of, which sugars, which acids and bases, et cetera, and so on. The next one is what they call FCC, Food Chemical Codex. What this is basically a safety manual. It says, okay, you don't want to have high levels of heavy metals, arsenic, lead, mercury. Anything that's in this codex, any kind of food that you will eat is actually in this document. So not just caramel color, anything. And it says you want to limit how much heavy metals are in the stuff so that way you remain healthy. So that's recognized by the FDA. And then lastly, the United Nations has their own thing that they've come up with and their own regulations, complementary to the United States. But every country actually has some of their own regulations. The EU has theirs, Australia has theirs, China, et cetera, and so on. But again, we're just concerned about just the organic coloring polymers. And they come in a variety of different sizes. It's not just one molecule, it's actually a family of molecules for each of the different classes. They come in different strengths, different color tones, and they also carry a certain amount of flavor to things. Some things are sweet, some are bitter, some are sharp, some taste like coffee or chocolate. Some are very mild. So when we're talking about color, we're talking about the visible spectra, right? The rainbow that you're always kind of used to. So for how do we, obviously none of this looks like caramel color. Maybe there's some yellows and some reds in here. but we're only going to focus only on a couple of different numbers. And we have to use an instrument to help understand that, and that's called a spectrophotometer. So a spectrophotometer starts off with a light source. It goes through a lens. It then goes through a prism to make the rainbow. But then there's a special part of the instrument called a wavelength selector to kind of narrow in on certain wavelengths. And in this case, for caramel color, we'll measure color at certain wavelengths. And then finally, that light then passes through a solution. So you got a sample solution there. And then based off of how much light comes through and comes out, it will give you a number. And it's what we call an absorbance number, or even a percent transmittance. So if you have a cloudy solution, you're going to have a higher value, right? Or a lower percent transmittance. So if you was to take a scan through the full visible spectrum of caramel color, it'll actually look like a ski slope, right? It's just a nice trending thing. If you go and look at one of the other types of colors, what they call FD and C dyes, red number 40, blue number 1 that you may see on a package of M&Ms, there'll be spikes instead of a ski slope. And they'll be at certain areas on that visible spectrum. Now, the other one, it says here, 10 base log, if you was to apply a mathematical operation, in this case, the log of that ski slope, it turns into a nice straight line. And we call that the Hue Index. The Hue Index is a number value to give us an idea of the redness, yellowness, and the darkness of the caramel color. So what is color? For us, it's color strength, and we're going to measure the color at 560 nanometers. We call that tinctorial power. That's at a specific concentration. So we're talking 0.1 grams to 100 mils of water, and then we measure that in the spectrophotometer to give us an idea of what that tinctorial power is. The higher the tinctorial power, the more color strength that's available to use in the different applications. Another one for an industry is called color intensity. It's just at a different wavelength. And then the Hue Index, where we talked about the color tones, the brownness and yellows, the shades of the color, it's just a mathematical operation of, again, a couple of the different wavelengths. All right, so that's fine on the math stuff. Let's actually see it in works. So what we have here is 5 different solutions. They're all weighed up the same way. So it's the same concentration, but you can see how the class 1s are so much lighter in color, so much more yellow in color, as compared to the class 4s that got the very nice dark color. And so it's about color strength in the slide. So how, does this slide also represent the color tones? Color tones are a little bit different. Again, we're talking about the shade. It's not just that it's yellow. So these two sets of samples here, one of a class 1 and a class 4. Again, class 1 has the higher hue. The class 4 has the lower hue. So higher the hue, the more yellow. The lower hue, the more brown. If you look at these are all to the same color strength. But the class 4s look more dingier or dirty as compared to the brighter class 1s that are above it. And then if you take the powders and dry them, they have the same kind of color characteristics. Applications. What do we use a lot of the caramel colors in? Well, it's the most widely used of all the different colors that you can use in the industry, both in food and in beverages. They generally use to enhance the appearance of your food. As well as you have to be concerned about a little bit of the flavor, because I mentioned sometimes they are sweet, sometimes they're mild, etc. Most of the time the caramel color, though, is going to be used for color, 99% of the time. You only have to pay attention to the flavor, just a small amount. And it can be in a variety of different things: pet foods, cosmetics, pharmaceuticals, beyond just food and beverage. I've even seen it used in tobacco, so strange things. But its applications are dependent upon those classes again. This chart here, I'm going to spend a little time on. So if you look at 1 versus 4, you can see that the color strengths are rapidly jump up with the 3s and 4s because they're using that nitrogen source, that ammonia. The class 1s and 2s, they have less color strength. They only have the 120 and 100 color versus the 360 and the 600 that the other ones have. They also have different ion charges. Those ion charges are very important. So neutral, negative, positive, negative, okay? Those kinds of things are going to tell you about how well it's going to interact with the different applications. And of course, then you get your taste aromas and everything else. Where the class 3's got the nice chocolatey flavors, the class 4's are mild, sometimes a little bit of bitter, but most of the time they're mild. Class 2's can be bitter to mild, class 1 sweet, bitter, etc. So for liquid applications, the things that most of the time it's about solubility. Is it going to be salt soluble? Is it going to be acid soluble, alcohol? Things dealing with proteins or tannins. When we're talking about solubility is if it's not going to be soluble, it's going to be hazy or it'll look like precipitate floating around in your drink. I'm pretty sure a lot of people don't want to pick up their soda and see a bunch of chunky stuff coming out of the bottle, right? So class 1's salt function is not a typical thing. It takes special processing to get that to happen. For being acidic function, they're not going to be phosphoric acid stable. So most of the time you're not going to see a class 1 used in a cola application. But you can see it in certain teas and other things because it has some acidic function if the class 1 process starts off acidic. But if it starts off basic, meaning that, having the high pH, the acid function goes down. So the alcohol function is just reciprocal to that. So if you're being more acidic, you're going to have a lower alcohol function. As compared to being basic, we're going to have a higher alcohol function. Proteins and tannins, it's just kind of a varied response because it's got what we call a neutral response because of its ionic charge. So sometimes it works, sometimes it doesn't. It's sometimes a lot of trial and error. So a lot of the things that class 1s are used in, it could be whiskeys, liquors, rums, lemonades, some teas, poultry coatings, for turkeys or chickens, some sauces, some flavors. These are some of the more typical applications. Class 2s, generally they're not known for its salt function. It's got some acidic function, but not quite high, but they've been used in teas and other things. Tannin functions are pretty good, but they have poor interaction with proteins. So you're not going to see it in like milk or beer, where it got a lot of different kinds of proteins and stuff in it. Alcohol functions are pretty good. So because of those, you're going to see them in liquors and teas, rums, again, poultries, light cake mixes. They got a nice, excellent red tone appearance to them. Class 3s, there's actually a variety of different processes you can do these things in, and because of those processes, you'll get different kind of functionalities out of them. So if it's a total atmospheric, remember those open kettles, you're going to probably have a very good salt function, beer function, and you're going to have high viscosity. But if you do a total pressurized reaction, so in the pressure kettle, you're not going to have salt, you're not going to have beer, but you're going to have good viscosity. It's going to be nice and low, so it's not going to be thick. So you can do a hybrid system where you partially atmospheric and then close the pressure later. Then all of a sudden, the salt function comes back and the beer function comes back. And then the viscosity is kind of in between. Alcohol function is not that great for class 3s, but beyond beer, who cares? So typical applications, cereals, pet foods, brewing, milk, meat sauces, cooking, dipping sauces, bakery, and then the list goes on and on and on. I've also seen class 3s used in tanning solutions. Spray on tans. Hey, I'm going to be, a good-looking president today. So class 4s, obviously, because we need to produce so much, we're going to use the pressure reactor because we've got to supply all this color for all the soda can manufacturers. Salt function is not a typical thing. It can be accomplished, but it's not very common. Alcohol function is generally pretty good. So I've seen them used in different liquors and other things. Acid function is excellent. Great phosphoric acid and organic acids, so it can be used in some ginger ales, obviously all the pops. Protein interaction is most of the time not very good, but the tannins are pretty good. So because of all those things, it's used in a variety of different things, mostly colas, but teas, baking goods, meat rubs, pet foods, cocoa extenders, coffee things. It has quite the versatility like the class 3s for applications. So typically if something doesn't work with a class 4, we'll try a class 3. And if the class 3 doesn't work, then we'll try the class 4, and we'll kind of go back and forth. Developing a caramel, my job. Mad scientist at work. I've got a wonderful lab, I got a wonderful staff, and I got a great company to support all of our work. Why do we need a caramel? You know, why do we need something new? Can't we just maybe choose something off the shelf? Sometimes that works, sometimes it doesn't. Sometimes we have to modify the product. You know, but do we need a new product? That's the common question I get. I like saying, yeah, we like to have a new product because we like to play around. Where do we want to start? Well, sometimes in the competition of things, we want to get the competitor's product and their spec, maybe even a sample, reverse engineer it a little bit. Sometimes there's a new regulation and we have to meet it, so we have to modify the process to make it work. Or sometimes we need to have a better application, or maybe there's a new application, you know, maybe a higher salt content, maybe it's got to be salt and beer functioning. I've seen all kinds of weird things. Choice of class makes a huge impact on this, and then the type of process. Are we going to use an atmospheric process, pressurized, or a hybrid? You can't just start working. You got to actually have a plan in order to get things to work. We got to define the project. We have to set a priority, because sometimes we have high priority with low priorities, things that people want tomorrow, other things, well, when you get time to work on something. Understand the time commitment, because sometimes developing products, sometimes it could be a couple days and it could be several years. R&D is not a regular formula to kind of put out. Management doesn't like that, but that's reality. Exploratory cooks, because we have to sometimes find out what works and what doesn't. Then after those exploratory, then we actually start then applying our math. We start generating up mathematical models and other things to see what influences this. And then finally we will do a predictor cook based off of those models, and then do a scale up. So we'll start off with a little bench walk, you know, maybe we'll have maybe a pound of a product, and now we're scaling it up to, 4,000 gallons. And that's where the production trial comes in. And then finally, we will then send the sample off to the customer and see, hey, does it work? Got a variety of different tools that we play with. We have our own pilot dryer. We got small reactors dealing with things. So again, very well equipped. But it's still a basic process. It's sugar, some chemical to make color. The problem is, for an R&D team, we want to make sure everything falls in, nicely in the center. If we have it underreacted, we're going to have the apple. If we have it overreacted, we're going to have a pile of goo on the production floor somewhere, which we don't want. That's a mess to clean up. So how do we control the reaction process? Well, we monitor a variety of different aspects during the reaction process. We will pay attention to our temperatures. We will pay attention to pressures, pHs, and obviously we're going to measure color. We do this periodically through the process until we actually reach a given point. The cycle of R&D is cyclic. Sometimes it's never ending, but sooner or later we have to pull the plug on a project. So success or failure? Well, it's about try again. As Thomas Edison said, I haven't failed, I just found 10,000 ways it didn't work. Challenges. We have a lot of those these days. We have always new regulations coming on board. We have new definitions for these things or that. So we're just going to talk about a couple of them are kind of related. One is natural versus artificial colors. What does that mean? And then the problem with trying to get a class 1 caramel to function like a class 3 or 4. We kind of touched upon that a little bit. So my question is, does this look appetizing? Come on, gray meat, ugly looking buns. Oh yeah, I just want to eat into some of that stuff. But everyone wants that nice looking label that says artificial color, Artificial color, or do you want natural color? Do you want something that's chemically added to something, or something that looks like those fruits sitting up there? Problem is, there's no definition of natural color. The FDA has refused to answer this question, and has left a lot of things undesirable. There's actually only 2 categories of color in the United States. They call it exempt and non-exempt. Boy, that tells you a lot, doesn't it? What's a natural source? Don't know what that definition is either. Is a process in which the color is made or extracted, is that natural? Is caramel color manufacturing, is that natural? Well, I showed you, nature examples. You bite the apple and it forms. But in order to get that, that beet juice color, did you know they go through an extraction, some filtrations? Does that sound natural? That's the question. What's natural? And here's another one to really drive your mind nuts. If you actually add a color to a product, is that product now artificially colored or naturally colored? It's artificially colored by the FDA rules. That's at least they gave clarification on that. If the product doesn't normally look like the way it is, and you've added something to it, it's artificially colored. No matter whether you consider it naturally made, naturally extracted, or whatever, it's artificially colored. And the problem is those definitions vary from country to country. Up in Canada, caramel color is considered natural. In Australia, caramel color is considered natural. But we have no definitions of natural in the United States. So, why use caramel color if the product is artificially colored? Well, you don't have to label it artificially colored. You can say caramel color on it. But still, why use caramel? I mean, aren't you artificially coloring something if you understand that definition? Well, but color is important to your senses. Again, think back to that nasty looking meat that I flashed up there. The old saying says, eat with your eyes, taste with your nose. You ever try to taste something with your nose plugged? Don't taste the same, does it? Same thing with eating something that's colored gray or whatnot. So natural versus artificial still. People still look down on artificial. Does the classic caramel process make a difference in the natural versus artificial debate? To me, that's debatable. But some people think that class 1s are considered more natural than the others because we're not using sulfite and ammonia. But aren't we using the acids as a basis? But class 1s, we can only use heat, right? If we decide to, we don't have to use any chemicals, just use heat. That's where the caramelized burnt sugars are about, where we're just applying heat. The problem is again, as you go from class 1 through 4, if you remember the slide, class 1s are yellow, class 4s are brown. You're not going to generate as much color, and you're not going to get those darker tones. And that's the problem with trying to swap out a class 3 or 4 with a 1 in application. Class 1s, we're typically 2 to 4 times stronger in color as compared to class 1s, which is very significant, right? Because now class 1s have got all that different flavors as compared to class 3s and 4s. Remember, class 4s are mild. Class 3s are, chocolatey, coffee kind of flavored. Class 1s were either sweet, burnt, bitter. And now if you're using 2 to 4 times as much, now that flavor profile starts carrying over. And that's when you have to be concerned about that flavor. Hue Index, again, I talked about the class 1s that got more of the yellows and reds. The class 3s and 4s are going to be more dark and more brown. So now when you're trying to, make that pumpernickel bread that's supposed to be nice and dark brown, and now it's got a shade of yellow to it, or maybe too much bright redness, it's not going to be the same. And you're going to look at the two different kind of breads, and you're going to probably choose the one you're most comfortable with, right? And again, the flavor. I already mentioned that. You're not going to bite into a bitter piece of a bread. When you get your microwave dinner, you don't want to taste all burnt because you've switched out a class 4 for a class 1. These are some of the problems we run into. Not to say that class 1 work hasn't done well in some applications, but these are the challenges we have to run into. And then we got the application limitations. Class 1s, again, dependent upon the process, could have some acid function, maybe not. May have some salt function, but may not. Class 3s are good for salt. They're good for the beer. The class 4s are really good with the acids and stuff. So depending upon that compatibility thing, that class 1 in those liquid applications could be floating precipitate. So anyway, I wanted to thank you tonight for your attention. If you guys have any questions, I'm more than willing to entertain them. Thank you.
So if you have a question, raise your hands. Okay. We'll take one question from this side, one from the other.
So how did you find your job working for this?
How did I find my job looking for this? Well, that was pure luck. Chemists are actually all over the world and for a variety of different jobs. You can find chemists in food manufacturing, water. You had the guy from NASA. There's chemists in NASA. So the way I went and found out about it, I hired a headhunter and got me a job.
Does the source of the sugar have any effect on the amount of caramelization?
Yes, it does.
Cane, wheat, corn?
Basically, if the sugar is sugar cane, so it's actual sugar, it will break down to fructose and dextrose automatically as soon as you apply some kind of acidity to it. You also are allowed to purchase what they call invert sugar, which is also part of that CFR identity. So because of that, the fructose is more reactive than the sucrose and more reactive than dextrose. So the reactions actually go a lot faster. The negative effects is that generally then the product has a poorer shelf life and then can generate extra byproducts that can cause a lot of extra issues. So pluses and minuses.
Do you think that someone could make caramel color just with home supplies, things you would find inside a house?
Yes. You can easily take your sugar that you've got sitting, in your mom's canister, put some in a saucepan, get some maybe some citric acid, which is probably maybe some vinegar and stuff. You put that in there, and you can actually start generating color fairly quickly. But just understand, you're going to make a pile of gooey mess.
Okay, sorry. So you talked about a lot of the food and beverages that you add caramel to. So if you think about pop or beer, is it colorless before you add the caramel?
No. Depending upon the process and the techniques, there will already be a color already in them. And so like in the spirits case, beers and whiskeys and whatnot, what it allows us to do is to have better quality control. So that way when you're picking up your bottle of Jameson's and everything else, it has consistent color. So that way when you go from one bottle to the next, they all look the same. Because if you see one that's a little bit lighter shade or the other one, did they do something wrong? Because as humans, we're very finicky. We like consistency.
happened to the gray meat and the gray buns?
What was that about the gray stuff?
What happened to them?
What happened to them?
Yeah.
Well, I just pressed the button and made it go away. No. What those were examples of generally microwave materials, because actually if you cook meat in a microwave, it doesn't generate color. So what they wind up doing is they do a couple of different food technologist tricks. One is they could use Maelard. Maelard will actually generate color with heat, or what they'll do is they'll pre-treat the meat with some caramel color. So, sometimes it'll look like grill marks on there. That's caramel color. They've actually just kind of dribbled it on there. So, the bread, who knows with what they did with the bread. But typically, it was just an example to kind of get your attention that you have an expectation to see that bread to being, white, or maybe some browns, or maybe a dark appearance, and not gray. What was that? It looked like Oreo cookies.
What's the most interesting part of your job?
What was that?
What's the most interesting part of your job?
What's the most interesting point of my job? Well, making something and the customer likes it. Because that's who's going to pay my bills in the end. If we don't have customers, all you guys, I'm out of a job. So if you like what you eat, what you drink, keep doing what you're doing, and I'm satisfied.
Are there any uses of these technologies outside of like food and drinks and medicine?
Is there?
Are there any uses outside of consumables? Like food.
Yes. Like I said, I mentioned a few of them, such as spray-on tans. I wasn't joking with that. They actually use a Class 3 caramel because it actually often stains the skin. I've seen it used in tobacco leaves. There was a gentleman who was trying to develop tobacco leaves, and the Class 3s colored it very well because it binds itself to all the proteins actually in there. I've used them in inks, so in jet inks. Seen them used in those things. So all kinds of weird stuff.
Would yellow caramel color be used in pop?
Yes. I've seen what we call our white T25, which has got the highest Hue Index, to be used interchanged with what they call, I think it was yellow number 1. So we've replaced FD and C dyes before. So yeah, yellow pop, can see it happen.
They don't put it in bag.
Caramel color, yes.
Does it not bring color?
That's a interesting thing about calories. So what they will wind up doing is using certain caramel colors that have very low carbohydrate residuals left. And that's where the old industry standard, what they used to call a double strength. A single strength. And the single strength had a lot of carbohydrates left. So then they wanted us to develop the double strength. So we doubled the color and we used up more of the sugar, so there was less sugar to be used in the dye drink.
How long were you in your job?
I've been there for about 20 years.
How much caramel color is in like a can of Coke?
They estimate about 0.2%. So a 1 drop of caramel goes a long way.
Any more questions?
Does caramel color, has it ever been found to have any addictive properties where
Addictive properties?
where
No.
individuals crave it?
No, there's no addictive properties to anything about caramel color. Except for it looks pleasing.
In your 20 years job, which one is worst, which one is best?
What was that?
In your 20 years job, which task is worst, which is best?
Which is the worst and best parts of my job? The worst thing is probably, we're working on a project and we've run out of time and options and we're not successful. Because because you've invested so much time and energy, and some demands are very difficult to be accomplished. And as I said before, as long as you guys feel satisfied and still buying the pop and still buying the things that got caramel color in it, I'm doing my job right. That is my best part.
Oh, hi, good evening, Michael. Thank you for the wonderful presentation, very informative. I got one question for you. So I wonder nowadays in the United States, what's the major sugar source? The sugar refined from
Corn.
Sugar cane or from corn?
Yep. Corn is basically, with enzymatic processes, brings out the sugar that we use. And in this case, it's dextrose corn syrup. And that's used probably for a good 90% of our business. So most of the sugars that are used in most of the colas and all that other stuff will be from corn. For those who are more concerned about like GMO issues and other things, then we'll use sugar cane to be, for those applications.
Hi, I'm sorry we missed the beginning of your presentation. Is there a way consumers can tell from the label what ingredients go into the caramel coloring? Like I've read the 4-mel is potentially not a great ingredient. Is there a way you can tell? Like when I read labels, it just says caramel color.
No, because caramel color is 100% caramel color. There is no list of ingredients. Now, there's a list of components that are defined that we can manufacture into caramel color because all those things get used up. So it's just now, by the federal government, caramel color and that's it. So 100% caramel color is what we make and what we sell. So if you wanted to look up to find out what we are allowed to use to manufacture caramel color, you type in 21 CFR 7385 into your web browser, and you'll see everything that we're allowed to make caramel color.
Do you believe that caramel color has made a positive impact on the community?
On community, yes, in a variety of different ways. I'm standing here right now talking to you about science, and to me, that's a good impact.
I missed if you mentioned, so the color that you add to the Coke products, does it add the sugar, the sweet part to the product or not?
No, Coke will use what they call high fructose corn syrup, and that's where the sweetness is coming in. The amount of caramel that is used, which is, I said, 0.2%, whatever residual sugars are in the caramel color, doesn't really add anything to the Coke product whatsoever.
Does the sulfite and ammonia burn off? Or how
Now that's a good question. So they don't necessarily burn off. They will decompose and become part of the caramel color. All right. So let's say that maybe someone's got a concern about sulfite because there's some people who have a certain amount of in some countries they call it an allergen, in others they would consider it a sensitizing agent. So if you have too much sulfite, but that's typically referred to as what they call free sulfite, so the sulfite that you would spray on like vegetables and other things so they maintain their greenness in the marketplace or for shipping and other things. Sulfite that we use is a chemical reactant, so it gets used up and is chemically bound. The only way it's going to be released, we actually do a sulfite test as required by the FDA. It goes through an acid digestion, so in order to release the bound SO2, so we can then say this is how much SO2 it contains. But it's chemically bound. It's not like just floating around like like gas or something. Same thing with ammonia. And the ammonia gets all used up, and it's chemically bound. And the only way it's going to be released is you have to force it out.
Chris, In the meantime, Jared, I'll appreciate if you can tell what you are going to cover in the part 2 of Roundtable.
Okay, so the part 2 that we're going to dive a little bit more into the mathematical models that go into manufacturing into a caramel color. So we're going to go a little bit more in depth about how to control the process, and then some of the modeling that we're doing, and then some of the shelf life stability tests that we do to make sure that the caramel colors are going to be viable for at least the near future once we manufacture it. So
we'll take one more question.
Have you ever used maple sugar to make caramel color?
No, that's actually not on our list, but that would be an interesting experiment to do, though.
Well, we will conclude here the first part of the Young Scientist Roundtable. As you know, that our next roundtable is on December 4th, where we have got Dr. Michael Osterholm, who will talk on the subject of deadliest enemy. He has written that book recently. If you have got a book and if you want him to sign, please bring the book with you. Continuing with our tradition here, we need to, guys, give me 1 second. Let's first acknowledge the effort that the speaker has put together here to come here from Iowa to talk about caramel colors. Let's have a round of applause. Here for you. Okay. All right, this part is finished. Have a cookie. If you want to learn more about it, come to the part 2, or otherwise see you on December 4th. Thank you.